In this lesson, we'll talk about applications of quadratic equations. We'll go over several word problems. The first one is a geometry problem. It will refer to similar triangles. Given these two diagrams of similar triangles, we need to find the length of the side AC. So this length. Remember, two triangles are similar if the ratios of corresponding sides are equal. So let's set up a proportion AC to DF, 3x minus 19 over x minus 3 is the same as CB to FE, so x minus 4 over 4. And then when we already have this proportion, to solve it, we can use cross multiplication. That means we're going to multiply these two expressions across, and this product will be equal to the product of these expressions multiplied across. So we have 4 times 3x minus 19 equals to x minus 3 times x minus 4. Okay, so now we need to release those brackets, multiply through, so we have 12x minus 4 times 19 is 76 equals, and FOIL these two brackets. So we have x squared, negative 3 and negative 4 is negative 7x, and then plus 3 times 4, 12. Let's bring everything to one side, starting with the highest exponent. So we have x squared, and then 12x goes to the right, so it's negative 12 and negative 7. That gives us negative 19x. And finally, 12 plus 76, that gives us plus 88 equals 0. And now we need to factor this quadratic trinomial. Let's see if we can guess the factors. Let's prepare two brackets. The product's supposed to be 88 and sum 19. Well, 11 times 8 satisfies these conditions, right? So we have x minus 11 and x minus 8. Therefore, our possible roots are x equals 11 or x equals 8. Is that our final answer? Well, let's go back to the question. We need to find the length of the side AC. AC is not the same as x. AC is actually 3x minus 19. So we have two possibilities. If x is 11, we have AC equals 3 times 11 minus 19, which gives us 33 minus 19, so it's 14. Or the second possibility, if x is 8, our side AC could be 3 times 8 minus 19, which is 24 minus 19, so we have 5. Okay, therefore our final answer is this side AC equals 14 or 5 units. So what we know about these two triangles is, in the case of x11, the sides of the big triangle and the small triangle are distributed as follows. AC is 14, therefore CB would be 11 minus 4, so it's 7. And then the small triangle, 11 minus 3 would give us 8 here and 4 over there. 14 over 7 is the same as 8 over 4. Well, that makes sense. However, in the second case, when x is 8, the sides of those triangles would be as follows. AC would be 5, and then 8 minus 4 is 4. In the small triangle, 8 minus 3 would be 5, and this is 4 as well. So the second case gives us triangles of exactly the same sizes, which obviously make them similar as well. The next example refers to the shape of a golden rectangle. What is a golden rectangle? This is a rectangle with the most visually appealing proportions. So what are they? Well, if we name the width of the rectangle by W and the length by L, the proportions of a golden rectangle satisfy the following condition. The ratio of the width to the length is the same as the ratio of the length to the sum of the width and length. We can visualize this situation in the following way. if this is the width of the rectangle, and this is, for example, the length of our future rectangle, then if we attach this length to extend the width this way, approximately the same much length, and then complete this rectangle like this, then the ratio of W over L, the width and length of this rectangle, should be equal to the ratio of width and length of the big rectangle, this one. So the width of the big rectangle is L, and the length is W plus L, right? Therefore, a rectangle is golden if the ratio of its width to length is the same as the ratio of its length to the sum of the length and width together. That means if the two rectangles constructed like this are similar. And this relation goes on. We could, for example, create another bigger rectangle by attaching this length over here and extend the big rectangle that way. So the ratio between the new width and the new length will still be the same. Okay, so that's what golden rectangle is. We wonder how to find the relation between L and W, so we really want to solve this formula for L. L appears in three places and in different levels. So the first thing to do would be to make sure that we don't have those denominators. Place all L's in the numerator. Therefore, the plan is to cross multiply. We would have W times W plus L equals L times L, so it's L squared. Okay, so we ended up with quadratic equation with respect to L. Let's multiply through the bracket and arrange the equation in decreasing exponents of L. So here we have W squared plus WL equals L squared. And then we want to move everything to one side. Let's move it to the right. So it will be L squared minus WL and minus W squared equals 0. Okay, so now we have very symmetrical quadratic trinomial. It is quadratic with respect to L, and it's also quadratic with respect to W. But let's focus on L. So to solve this equation, we are using quadratic formula. L1 or 2 would be equal to negative b, but the b coefficient is negative w, so negative b would be just w. Then plus or minus square root of b squared, so negative w squared, meaning w squared, minus 4 times a, which is 1, times c, which is negative w squared. Okay, everything over 2 times a, which is just 2. Okay, is it anything to simplify within this radicand? Well, yes, it is. This will be plus 4w squared and another w squared, so altogether we really have 5w squared under the root. So we have w plus minus square root of 5w squared, everything over 2. And now we can take w out of the root, so we end up with w plus minus w root 5 over 2. Now, if we factor the w outside of this whole expression, we end up with 1 plus minus root 5 over 2 of w, isn't it? That tells us that the proportion of length to width in a golden rectangle is this much. And since the length and width are both positive quantities, we'll consider only the expression with the positive sign. Okay, therefore we can claim that the length equals to 1 plus root 5 over 2 times width. What is the approximation of this coefficient? Well, let's use a calculator. This turns out to be approximately 1.618 of W. Okay, so this is the golden ratio, 1.618. Notice that this number is very similar to the ratio between a mile and a kilometer. 1 mile is approximately 1.61 of a kilometer. So to imagine a golden rectangle, it's enough to imagine a rectangle with one side being 1 kilometer and the other side being 1 mile. Isn't it interesting? We could find the golden ratio, the indicator of the most beautiful geometric proportions in the relation between the imperial and metric systems of measurements, even though they were developed independently. Here we have a motion problem. Two ships leave port at the same time, one heading south and other heading east. So one ship goes this way, the other that way. Several hours later, they are 170 miles apart. If the ship traveling south traveled 70 miles farther than the other ship, how many miles did they each travel? So using this diagram, if we find x, we would know the distance of this first ship and the distance of the second ship. Since the two pathways are perpendicular, we are going to take advantage of this right-angle triangle, so the plan would be to use Pythagorean equation. We do know that after those several hours, they are 170 miles apart. That means that this distance is 170 miles. We also know that the ship traveling south is 70 miles farther than the other ship, so if the distance of the first ship is marked by x, the distance of the south ship will be the same x plus 70 miles. So the diagram gives us already the expression representing the other distance. Okay, we can use this information and set up Pythagorean equation. We have x squared plus x plus 70 square equals the hypotenuse square, which is 170 square. So let's raise this bracket to the square. We'll get x squared plus, and we apply perfect square formula, right? So x squared plus double the product, which is 140x, plus 70 square, that gives us 49 and 2 zeros, right? Equals 170 square, or let's bring everything to the left, that gives us negative 170 square is 28900. Let's use a calculator here. Okay, we can collect like terms, so we end up with 2x squared plus 140x, and these two numbers together gives us negative 24,000 equals 0. Now, before we start either factoring or using quadratic formula, we could decrease those coefficients by dividing the whole equation by 2. So we end up with x squared plus 70x minus 12,000 equals 0. And it happens that this could be factored, so we don't really have to use quadratic formula here. We can get x, and then the product is 12,000, but the difference is 70. So what kind of numbers will multiply to 12,000? Well, 12,000 could be 120 times 100, right? But these two numbers would differ just by 20. So what we are searching for is a pair of numbers that will differ a little bit more. They are more apart from each other. Okay, if we take 80 instead of 100 and 150 instead of 120, then the product will still be 12,000, and our numbers differ by 70. So these two numbers would work. Okay, since the larger number must take the middle sign, so we'll get x plus 150 and x minus 80. If you have any trouble to find these numbers, obviously you could use quadratic formula, and that will lead you to the same solution. So our possible solutions are negative 150 or 80. Since x represents distance in miles, then our answer is in miles. And obviously our distance can't be negative, so we have to exclude this possibility. The only answer is 80 miles. Okay, so we can give the final answer. The east ship travels 80 miles, while the south ship travels 80 plus 70, so it's 150 miles. And then it's done. Next, we have a geometry problem. The outside of the mosaic mirror frame measures 14 inches by 20 inches, and 160 inches square of mirror shows. Find the width of the frame. Again, we have a diagram that helps us. We have the length of the frame, 20 inches, the width, 14 inches, and we look for the width of the frame from here to there. Let's call it x. The width of the frame is assumed to be the same around the frame. So x is everywhere here and there and there. Okay, to find this width x, we can use the information that 160 inches square of mirror shows. That means the area of the smaller rectangle, the inner rectangle, is 160 inches square. How do we find this area? Well, by multiplying the length and the width of the small rectangle. But how much is this distance from here to there? Well, it is the 20, but we cut off the two x's from both sides. So the length of this rectangle is 20 minus 2x. Let's record this. Area equals the length, which is 20 minus 2x, times the width. What is the width? Well, again, that's this distance from here to there, which is 14 minus the 2x. So this distance is 14 minus 2x. Okay, 14 minus 2x here. And this area is given to be 160 inches square. So here's our equation. We need to solve it for x. Since the numerical coefficients are all divisible by 2, it's useful to factor the 2 from each of these two brackets. So it will be 2 times 10 minus x. And from that bracket, we also have 2 times 7 minus x. And these two, instead of writing in front, I'm going to write in front of everything. So 1, 2 comes from this bracket, the other 2 comes from that bracket. Then we can see that the whole equation can be divided by 4, making it a lot easier to calculate, right? So we just need to multiply these two brackets equals 40. So let's FOIL. We'll get 70 here. Minus 7x and minus 10x is minus 17x. And then plus x squared. Let's bring the 40 to the other side and arrange in decreasing order of exponents. So we get x squared minus 17x plus 30 equals 0. Can we factor it? Can we find two numbers that multiply to 30 and add up to 17? Yes, we can. 2 times 15 would work. So x minus 15 and x minus 2 equals 0. That means that our width x could be 15 inches or 2 inches. Which one would work? What do you think? Well, since the overall width of the whole picture is barely 14 inches, we can't have the width of the frame to be 15 inches. That's basically too large. That's why we have to exclude it. It's not suitable for geometrical reason in this problem. So our answer is just 2 inches. Let's give the formal answer. The width of the frame is 2 inches. Let's see one more example. Use the compound interest formula, which is given here. A is the amount equals principal, and in the bracket we have 1 plus interest rate r squared. To find the interest rate r at which a principal P of $10,000 will increase to the amount 10,920.25 in 2 years. So basically we need to use this formula, plug in all information that we have, and solve for r. Our amount is this much, so we start with it, 10,920.25 equals the principal, which is 10,000, and then we have 1 plus unknown r square. The square is just because of these 2 years. Okay, we need to solve for r. How to do it? We could raise it to the square on this side and then use our strategy with quadratic equations. However, it's easier if we just divide those coefficients, divide by 10,000 to the other side. That just moves this decimal dot 4 places to the left. So we really have 1.092025 equals 1 plus r square. And instead of raising it to the square, let's apply square root on both sides of this equation. So square root will cancel the square, and since we know that 1 plus r is positive, we'll just write 1 plus r without worrying about absolute value here, equals, and square root of that number using calculator gives us 1.045. So r by itself, when we subtract the 1, ends up to be 0.045. This is the interest rate given as a number. If we convert it to a percent, we have 4.5%. We move the decimal dot 2 places, right? So the interest rate used in this situation was 4.5%. The last problem refers a little bit to geometry, but in essence to functions. Let's see. A sphere is inscribed in a cube as shown. So the sphere is touching the cube here and there, right? At the middle of each side of the cube, there is a point of tangency. Express the surface area of the sphere as a function of the surface area S of the cube. Okay, what do we know about the surface area of a sphere and a cube? Well, surface area of a sphere, let's call it SO. So let SO represents the surface area of the sphere, and S by itself will represent the surface area of the cube, as stated in the problem, right? Okay, we want to express the surface area of a sphere, so we want to see SO as a function of S. So SO of S. How to do it? Well, first of all, how can we connect the two formulas for the surface area? If we introduce r as a radius for the sphere, then in terms of r, the side of the box would be 2r, isn't it? Let's recall the formula for surface area of a sphere with respect to r. That is 4 pi r square. And the surface area of the cube with the side 2r is 6 times the area of one face, which is 2r times 2r. Therefore, we have 6 times 2r square. But that is the same as 6 times 4r square. Now we can observe that there is a relation between these two expressions. We have the same 4 and r square, isn't it? We have 4 here and r square as well. So the only difference is that the surface area of the sphere has the factor of pi, while the surface area of the cube has the factor of 6. So how to relate them? Well, if we solve this equation for 4r square, let's do it. 4r square would be equal to the surface area of the cube divided by 6 from this equation, right? And then we can replace this expression 4r square in the first equation by s over 6. So using the first equation, we could say that surface area of a sphere is the same as, we can copy the pi, and then instead of 4r square, we can write s over 6. So pi times s over 6, which really means surface area of the sphere is pi 6 times the surface area of the cube. So surface area of a sphere was expressed as a function of surface area of the cube. That means that the surface area of the sphere is approximately half of the surface area of the outscribed cube. Let's rewrite it here again. Surface area of a sphere is a function of the surface area of the cube through the formula pi 6 times surface area of the cube.